16.1 introduces vector fields, but I don't quite want to do vector fields yet because this idea of a path integral doesn't use vector fields, so I wanted to introduce that a little bit differently. So we're going to talk a little bit about path integrals first, which is covered in 16.2, and then after talking about path integrals, I think we should be able to talk about vector fields. They're not that related. But when we do another type of integral, we're going to integrate vector fields. And the way we're going to integrate vector fields is that we're going to bring it back down to make it look like a path integral. Now, the book doesn't call it path integral at all. I don't think the book even uses the term path integral. But I do want to use the word path integral or use the term path integral because when we start talking about all the different types of integrals, there's different analogies. Their integrals are analogous to one another, and I want to point that out. Okay. So somebody asked, what's the highest integral we're going to go to? We went up to triple integrals in terms of the number of integral signs. That's going to be the highest we're going to go up to in this class. But the other types of integrals that we're going to cover are going to be a little bit different, and I'll put a new twist in your idea of a multiple integral. So before we talk about path integrals, let's talk about a regular integral from Calc 1 or 2. Calc 2 integral. And we saw the Calc 2 integral as the area under the curve of some function f of x from a to b. So this is integral from a to b of f of x dx. And for now, I'd like to even shorthand this into, instead of saying a to b, maybe I'll call this an interval. Call this interval I. So this is an integral over the interval of f. I'd put dx there, but I'm just going to leave it like that and just say this is I should write that down. Integral of f over the interval I. So this is how we would think about it, or this is how we would say it in words. The integral of f. So that's our point of view so far of what we know as our single integral in Calc 1 or Calc 2. All right. So now let's take this into 3 dimensions, but let's take this into 3 dimensions in a flat way. I don't know. What? Let's see. I had this idea last night. And just now that I'm thinking about it, it sounded a lot better last night than it's doing now. But yeah. So let's imagine trying to do a similar thing here with a function f that takes 2 variables into 1 variable. So z is equal to f of xy. And let's imagine this interval. Let's take this interval, this very same interval, maybe going this way. And then let's say we want to find the area under the curve, except instead of a curve, we actually have a surface now. So let's bring this up to the surface. And imagine finding this area under that surface, but just along this interval. Does that visual make sense? So what we're doing is we're essentially, if we want to look at this using Riemann's sum and all that business, what we're doing is, let's see, let's focus on this interval. This is that interval over here, blown up. And then we can think about breaking this up into partitions. And then we have some delta something. What should we call it? I guess this is going along the x. We can call it delta x, I suppose. I'll just call it t, delta t. Yeah, it's just this one. And so I know this is an x-axis, but I eventually want to generalize this, so I'm going to call it a t-axis. And this interval over here that we're looking at would have gotten partitioned. And so since I'm calling it a t-axis, we can call this delta t. And then so that delta t would be the base, and then the height would be putting some point here. Let's call that point t star. It could be the left endpoint, the right endpoint, or the midpoint. And this particular t star, I guess, could possibly have x and y values, right? Because it looks like I can't just put t in there. I have to put x and y. So maybe the t star would have a corresponding x and y value. And that is what's going to go into the function. And it goes into the function, it'll give me a height. So the height is going to equal to f of x I star. I'm throwing a subscript in there because there's a bunch of them. Y sub I star so then our integral will eventually become an integral over this interval I of f of x I, or I guess xy, and then dt. Our delta t will become a dt. And that, for this, remember, we have to assume that x and y are going to be dependent on t. So after we kind of parse this out, we're going to eventually get a function of t, and then it'll look like just another integral. Okay? So what we could do is we can generalize that a little bit more and continue thinking about this as an area. So I'm going to start a new page here, but I'm going to redraw my setup, but instead of integrating over a straightforward interval like we did there, Well, let's integrate over something a little bit more random. So I'm going to set up another scenario here with my beautiful function. But now, instead of an interval that's going along an axis, maybe I can draw another interval somewhere else, randomly on the xy plane. Hell, it doesn't even have to be an interval. What if we just draw any curve? Any curve. Let's call this curve C, C for curve. And then imagine this whole business that we've been talking about as an area. So to kind of capture this area, what we can think about is putting this and projecting it up to the surface. And finding the area that this is going to make from the xy plane up to the surface. So the surface up here each point, if we take a look at a little sub-interval break over there, we can take a look at this going up to the surface. So what do we have here? We have the curve C. On the xy plane. And if we kind of think about C as a curve, how can we express C? There's a lot of different ways to express curves, right? But the way we draw curves out, we've been using, what's that called? Parametrization. We parameterize, what symbol do we use for parameterization? Do you remember? T is a parameter, but we have a letter that we use a lot for, what? L, we usually like to use L if it was a line. S, Q. I know we've used R for radius and stuff like that, but we've also, remember R a long time ago? Yeah. The path. So curve is really just a path. Hey, we're doing path integrals. Whoa. Coincidence? I think not. So our R is a vector of two functions, x of t and y of t, and they would parameterize our curve. So we would have a two-dimensional path going on here. And so that x of t and y of t that we were referring to in the previous page is now kind of coming to life here with this parameterization. And so if we get this set up like we've done before, we can do our blow this up business and then take a look at the partitions. Except it's going to be hard calling it delta t. It's not quite delta t. Because remember, oh, are you guys taking notes in pen? Remember that we want to think about t as an axis, let's say going from A to B. And what we want to do is this is a parameterization for t, so we want the A and the B for the t limits in your interval t to draw out that curve. So this is an x and y point. Let's call it x naught, y naught. And that would be the point that you would get if you put A, t is equal to A, into your parameterization function. Does this make sense? Okay, let's keep holding on with this abstract idea, and then we'll bring it back into an actual example that will hopefully be clearer. So imagine your starting point to be R of A, and if I put A, a number, a scalar, in for t, I'm going to get x of A, and I'm just going to call that x naught, and then y of A, and I'm going to call that y naught. And then I'll do the same by putting B in there, R of B, that B value from your t, and that goes into my parameterization, and then I'm going to get x sub E, B. I call it 0, so that's kind of weird. What? F? Oh. E? I don't know. Ah! Why am I calling it E? I just... Okay, give me a letter. M. Y. I don't know why. Anyways, that's just my ending point. I was going to call it E for end, but that doesn't sound good. E for end. End. Starting and ending.
X sub n. Y sub n.
All right. So, do you understand that the parameterization is like an intermediary? I mean, it's part of the drawing, right? But what we're going to do is, as we're drawing this, we're going to definitely use this parameterization. But then, when we finally break it down, we're going to look at the t-axis with a lot more detail. In other words, whatever this integral is going to look like, in the end, we're going to have an integral from A to B, and that's coming from our t-axis. All right, let's keep going with this idea. Now, if I want to take a little piece of rectangle here, the bad news is that when this was a straight line and I was just pretending that that line was t, then that's just delta t. But unfortunately, this is the base here is no longer delta t. I think it might be easier to talk about the height first. So we can take a look at the area of this thing, which is what we're going to add up. We're going to add up an infinite number of them, the Riemann sum business. The height of that is that if we take some random t value here, t sub 1. Oh, I'm sorry. I got this in the wrong place. I want my t sub 1 somewhere here. And then if I put that into the line, then r of t sub 1 is going to give me some x sub 1. I guess I should have said I. Let's use I. Y sub I. The 1 kind of looks like an I. Just put a dot on top of that. So if I take that random point, whether it be an endpoint or somewhere in the middle or anywhere in that interval, if I put that up on the function, that's going to give me my height value. So my height is going to equal to the function evaluated at x sub I, y sub I. And since we are kind of breaking this down to make it look like rectangles, the area is going to be easy, space times height. So the height we found, the base, this is the one that's a little bit more tricky. So the base is no longer delta t. So if you imagine partitioning this interval, or this interval from A to B, our delta t is over here, which is clearly not this business. So now, how would we relate this delta t with this thing? Well, how would we relate that? Yeah, we're trying to find this little distance over here in the curve. Well, that comes from this delta t. So we have a delta t over here. This is delta t. And then that gets translated into this little length over here. Oh, it's a length, right? Length. Length. I don't know, length. We could. We could. What if we just had 2 points? Let's say this is one of our points, x sub I, y sub I, and then let's pick another point, x sub I plus 1. I was going to say minus 1. But yeah, it's the same thing. So based on our partition, 2 adjacent points. You could make a vector out of that, or you could just find the difference and stuff, right? So let's find the difference. So to find our base, I need to blow this up now. Let's see if we can blow this up. Now, this is a curve, right? It's not a line exactly. Maybe I like Aaron's idea better. What if we make a vector out of it and find the magnitude? It's going to come out to the same thing. This isn't quite a straight line. It is just a curve. But what would be a good vector to describe this curve? Does that question make sense? The tangent vector. Yes. So the unit business is going, the delta t is going to help us shrink it down to whatever. So let's take a look at the tangent vector here. And the tangent vector might be longer. And so the way we're going to control the tangent vector to make it come up to be the distance that we want is we're going to multiply by delta t. So this is a tangent vector. What's a tangent? Tangent. What's a tangent vector for this? Well, we're going to want the magnitude of this vector. It's the derivative, right? So this is r prime of t. And then if we just throw the magnitude, oh, it's r prime of t dt. But if we throw the magnitude in there, I'm going to put sub I. But if we throw the magnitude in there, the dt is of some positive distance. We can take it out of the magnitude, and then it'll be there. So this is going to be our base. Okay? So based on what we've done so far, I think we're ready to define what's called a path integral. And our path integral is a symbol to use for a path integral. We're going to say this is an integral of f over a curve C. So before we said the integral of f over an interval when we're looking at an interval. Here we're going to look at this. A path integral is going to be in quotes. It's the integral of some function f over a curve C. So that is our definition for a path integral. And this path integral relies on a parameterization. So whatever curve we're dealing with, we're going to have to find a parameterization that describes the curve using t. So after parameterizing your curve with some parameterization r of t, this integral, which doesn't seem to make much sense at this point, will change into an integral now. When you parameterize your curve, you have to know a starting and ending point. And so you're going to have a starting point A and B from your parameter t. And then it's going to be base times height, where the height is going to be the f function. Now, instead of putting x and y here, where did x and y come from? They actually came from r of t, right? So that's the height. It's a composition, as you can see, times the base. And what was the base? The base we decided was the magnitude of r prime of t dt. The delta t becomes a dt in this integral. Now I put this symbol over here, dot. Is this multiplication or is it a dot product? When you take the magnitude, it becomes a scalar. And f is a function that takes two variables and the output is a scalar. So this is a scalar, this is a scalar, and so this is a regular multiplication, not a dot product. And I need to point that out now because our next integral will be a dot product. Okay? This here is a path integral. F is a scalar function. And R is the parameterization of a curve. Let's do an example. And for an example, let's say, let's find the integral. Find integral of a function f of x, y, and let's take the hyperbolic paraboloid. Over, now I need to come up with a curve, and I'll just say over the circle, the piece of the circle in the first quadrant. Okay. So maybe I might write it like this. It's going to be the integral of c of f, and they call it ds or dr or ds. Well, they call it S because it's like with respect to arc length. The S stands for arc length. Yeah. So this is a symbol that they use. I hadn't been putting the DS, but I think it's good to start introducing this now because when we talk about those other integrals, you're going to have like 5, 7 different integrals to look at. And there's going to be clues as to what type of integral that is just by looking at this thing down below. What are you integrating over? The function that you're dealing with and the differential that's involved here. So these 3 things will give you some idea of how or what type of integral you're dealing with. Sometimes those double integrals and triple integrals, sometimes they just write one integral for that and then they expect you to figure out what type of integral that is, if it's a double or a triple, based on all the other pieces of information. And just to make it easy, I just tend to, if it's a double integral, I put 2 integral signs. Okay. We're going to have 2 more different types of double integrals to deal with. All right, so we have our function that we're integrating, and now we want to figure out how to parameterize a curve. So that's one of our first steps is when you're dealing with this thing, you have a circle in the first quadrant. I need to know how to parameterize that curve. So let's draw the circle in the first quadrant. A radius 2. So the question is, what is this going to be? X. Let's just put R of t. R of t is equal to, I need an x and a y component. So what do you think? Circle, right? Ooh, did we forget how to parameterize? Yeah.
Solve for x or
Cosine t, sine t.
yeah.
What's your radius? 2. So 2 cosine t sine t, 2 sine t. Just testing. As part of parameterization, whenever you parameterize a curve, it's important to know when you're starting and stopping also, because this is really what's going to control the limits of our integration. So from what to what? So if we go from 0 to pi over 2, this will take care of our quarter circle in the first quadrant, right? All right. So that's it. Well, that's not quite it. We just have to plug in the pieces. According to our formula, what else do we need? We have this thing. We need r prime, right? And then take the magnitude. So this thing, if you remember, becomes an integral from a to b of f evaluated r of t. And what this means is I have to take my x and put it in for x in my f function, take my y, put it in for my y in my function, and then that'll take care of that. And then I need to multiply this by the magnitude of r prime, so I need to take the derivative of my parameterization and then change that into, and then take the magnitude. All right, so let's do the pieces. We need r prime. What's r prime here? So minus 2 sine t, positive 2 cosine t, and we need to finally take the magnitude of that. Squared, under square root, take it out, blah, blah, blah. Can I just say 2? Okay. So it's the square root of each of these components, quantity squared. There's a lot of steps here that I'm going to skip. All right. So that's the r prime part. And now we need to figure out what happens here. And if there's any possibilities or hopes of simplifying it, it would be great. If not, then we're just going to have to deal with that. So you're going to need to put the original r, the x and y for r in for x and y up there. So this is 2 cosine t quantity squared for my x, 2 sine t quantity squared for my y. And if you know some formulas with the sine and cosine, this is like a double angle formula or something like that for the cosine. But if you don't, then it'll just be that. So now we have an integral, and we've established our limits from a to b. That's 0 to pi over 2. Now we have our f function evaluated at the parameterization. So we've got 2 cosine t squared minus 2 sine t squared. And this whole thing is going to be multiplied by the magnitude of r prime dt. And now it's just a regular single integral that we know how to deal with. Okay? This is what I was going to talk about on Monday before your test. That would have probably not have been good enough. All right, at this point, it's all just calculus, so you can just deal with that. It's just an integral. But it's a regular integral now that we've seen in Calc 2. Okay? So how did this work out for you? Okay?
So the path always gonna be polar coordinate?
No. It could just be a straight line. Oh, we could do one of those. Do I want to do one of those? All right, let's do one of those. Let's do another example then. I just make up some weird function. X plus y minus ln of, I don't want to do any ln's. That might lead me to some issues. Let's go x squared y or something weird. It's not really that weird. Oh, this might get negative. It doesn't matter. This is some function, whatever it is. C is a combination of the line segments from 0, 0 to 1, 0 to 1, 1. So, yeah. So sometimes we have problems where C isn't just one smooth curve. C is a couple of pieces of curves. And in this particular case, we start off with 0, 0, and then we go to 1, 0, and then we go to 1, 1. So in this case, we're going to have two equation or two parameterizations that we're going to have to deal with. For this problem, for these path integrals, it turns out that the orientation doesn't matter, like your starting and your ending point. But for future integrals, it will matter. So why don't we just get used to describing a path when we're drawing it out, to include the arrows to tell us which direction we're going. In this case, we're going from 0, 0 to 1, 0, and then we're going to go from 1, 0 to 1, 1. So those little arrows there tells you the direction in which you're going. Like I said, for this particular scenario, the direction's not going to matter. So the orientation is not important, but later on it will be. So it looks like we're going to have two functions. Our integral is going to have to come up with two different integrals. So let's break this up to C1 and C2. This is a C1 part. This is a C2 part. So let's parameterize C1, R of t. And of all the things that you need to be able to parameterize, lines and circles are like most important. And then the other, you're going to have to deal with other types of curves that you'll eventually get to parameterizing. But parameterizing a line is essentially going from one point to another point. Now there's a little formula for that a while back that we saw that you guys probably forgot already, but that's what we need. Kind of like the distance formula. Has something to do with like AB and A minus B and something like that. What? Yeah, 12, 13. I think it's in 13. So anyways, to think about parametrizing lines, I usually just, if I have 2 points, which is what mostly will be happening for us, it's going to be the starting point is 0, 0, plus t times the vector from the starting point to the ending point. So I need to do a subtraction there, the head minus the tail. So the head in this case is 0, 1, and then the tail in this case is 0, 0. So I don't know if that ever became a fancy formula for us, but this would be a way to parameterize a line. It's, wait, Cameron?
That's the definition of the line.
Oh, yeah, I guess so, yeah, if you want to think about it. Mimi, what did you say?
Wait, why is the head 0 1?
That's the tail. Head minus tail. Oh, 1 comma 0. That look good? All right. I suppose we could simplify this and then make it into, the separate x and y. So this is, the x component is 0 plus t times 1. And then the y component is 0 plus t times 0. And remember, when you're dealing with this, it's important to figure out our limits of integration too. So when we do this parameterization of a line, as Cameron said, it was a definition. Per the definition, this is always going to be from 0 to 1, which makes it easy for us to remember. So our C1 will have limits from 0 to 1. And so will our C2. I guess I should call this R1 and this is R2. And so R2 now starts from 1, 0 to 1, 1, and then it's going to be 1, 0 plus t times head minus tail, 1, 1 minus 1, 0. All right, so how is this going to look like? It's 1 plus, that's 0, right? So it's just 1 plus t times 0, and 0 plus t times 1. And again, it's going to go from 0 to 1. Okay? Now thinking at our components, we need, what do we need? We need the derivatives and the magnitudes of the derivatives. So let's do that. R1 prime. So with lines, it's nice and easy. It's really just a direction vector. So take the derivative, it'll be 1, 0. And it turns out that the magnitude of that will just end up being 1. And similarly for R2, The direction vector here is 0, 1, which also has a magnitude of 1. Now, these three examples that we're working on, the magnitude turned out to be constants, but that's not always going to be the case, just so you know. All right. So let's write our generic path integral. So this is an integral over a curve of a function ds. And we said that we were going to split this up to two different integrals, c1 of f ds plus c2 of f ds, where c1 is that first integral going from 0, 0 to 1, 0, and c2 is that next line segment going from 1, 0 to 1, 1. Okay, so let's put those in. Our r, wait, I don't know if I want to do this yet. Let's see what happens when we put r in here, r1, f of r1 of t. So r1 is t comma 0. And if we put t comma 0 in here, we're just going to get t plus 0 minus, well, that's going to be 0. So that's just t. Okay? So that will go in here. So we have the integral of f of r1 is t, and our ds turned out to be the magnitude of r prime times dt, and this is going to go from 0 to 1. And then the next one, we need f of r2 of t. R2 is 1, 2. What? You get it? So.
Yeah, finally somebody laughs at my joke.
So we have 1 comma t. And so we put 1 in for x and t in for y. 1 squared times t. So this is just going to be 1 plus t minus t, or minus, that's just going to be 1, right? T minus t. So that turns out to be 1. And then the ds, again, will become 1 times dt. And this is going to go from 0 to 1 because that's the limits that we got. All right, well, this is easy enough to do. Probably do it in your head. But that's how you would do that integral. So you would have this path integral that's broken up to these two paths, and you would do each of those paths separately. My work is all over the board here. Should have tried to make this more linear, but okay. Is that Doable? All right. So let's take a look at this thing again where I tried to make that relationship, and we could just make one more thing clearer in this definition. I kind of like to think about it as a symbolic definition or symbolic notation, and then a working definition. So let's do one quick summary page over here. So path integral is basically an integral of a function, and I'll include more integral of a scalar function z is equal to, I'll write it a little bit differently, also f, and then I'll put that notation R2 to R. So integral of a scalar function over a curve C in 2 dimensions, and the 2 dimensions has to be the same as the dimension of the input function, is denoted by integral of f over c with respect to the arc length. And then the working definition, I'll just rewrite what I had earlier from A to B of f of r of t times r prime of t dt. And so the other bit that I want you guys to make a relation with is the ds differential becomes this r prime. So now if we think back, it actually is the differential when we're taking the arc length. We're integrating with respect to arc length, so that differential is exactly the arc length. Yeah, remember the arc length, which is the square root? Now, all our arc lengths have been constants, but really the arc length, if you remember, is equal to the square root of x prime of t squared plus y prime of t squared. Okay? So we're integrating with respect to the arc length. And you know what's cool about this? Can I get you tomorrow? Oh, okay. This is Emily. Say hi. So what I was saying is that, you know what's cool about this is that you can bring this up to 3 dimensions also. Can you show them the top? Thank you. So imagine what would happen if you bring this up to 3 dimensions. terms of the notation, nothing. There's no change. It looks exactly the same, except when we're dealing with f. F is going to have x, y, and z, but then your curve is in R3, so that'll also have an x, y, and z. So it's the same thing, right? And the magnitude, instead of x prime squared plus y prime squared under a square root, it'll just have three components, x prime squared, y prime squared, z prime squared, all under a square root. So what's nice about this is that it's the exact same notation, exact same process, except you're throwing in a third variable. So we didn't have to add on, quote, add on another integral, because it's all kept neatly in this notation. All right, that's a lot to think about. You can think about it. Your labs, it would have been good to have the labs be due today, but are those labs for Chapter 16 set up yet?
Yeah.
Did I put due dates? Okay. No. So we're going to have labs due on, there's no homework due, there's some homework due from Chapter 15 on Sunday. Is there? Maybe not.
No.
But I'm going to want you to have the labs done by Monday before class. So I can either set it Sunday at 11:59 or Monday before class at 12, whatever class starts. 12:45. Monday at 12:45? Okay. Pretend that it's due on Sunday at 11:59, but I'll make it due Monday at 12:45. And these are the labs for the first few sections, 3 sections in Chapter 15. All right, so be ready for that.
So, are you going to do the thing where we write about our the test again and get the 5 points?
Or 7 points.
Oh, you want to do 1 point for this one?
Yeah,
No.
7's are really good.
No, I do not. You guys had 3 extra possible points from one worksheet and 2 extra points from another worksheet. And yeah, so you guys had a lot of extra credit. And then these extra 5 points.
Oh,
So
we do need to do the 5 points.
I'll get that working.
Oh, yes,
awesome.
thank you. You rock. So then when do we do corrections? Just wondering. 'Cause I know you give corrections for one of the tests.
Yeah, so, yeah. I'll post that over the weekend, and we'll probably be doing in a couple of weeks.
Oh, or don't we take it in class? Oh,
Wait, what are
take
the
it?
corrections? You just like correct it, and then we get 100%.
You redo the whole test at home in your own time.
And then we get 50% of the
And I'll take the average between
Oh.
your score and this score.
Thank you.
Awesome. Okay, thank you.
Sure. Not counting the extra credit.
Yeah, you add on extra credit after?
No.
No. Oh, so if you do corrections, you don't get extra credit, but like you get the correction. Okay, I see. So say. Okay. Thanks. Come on, Rick. Always late. Let's go. Yeah, you're always late. Were you taking a shower today?